Experiment 8 is about separation and identification of an unknown mixture. The primary objective of the experiment is to separate and identify a carboxylic acid, an amine, and a neutral component, which is either an alkane, an alcohol, a ketone, or an aromatic compound in a mixture using liquid-liquid extraction. The flow chart for the experiment is shown in the second page. So this is the liquid-liquid extraction separation procedure. I will now be doing the first part, which is starting from the unknown, and then I'm gonna add a solvent and then add a base. So the first part is indicated in here. So again, the first part, we'll start with the unknown. I'm gonna put in a beaker, and then I'm gonna add solvent, which is ether, and then I'm going to add a base so that we can do the extraction. So I'm gonna refer to this page, or I'm gonna refer to this flow chart. This is also a schematic diagram of the procedure, and I'm gonna refer to this diagram while I'm doing the experiment. This is the sample that we're going to be using for the experiment. So typically each student will get one unknown, and it's labeled as a number. And we put it in a amber bottle, amber jar, and then it's has a screw cap. Okay, so the three components are inside mixed together. So I have everything in here. I have the base, which is sodium hydroxide, 3 molar sodium hydroxide. And then I already measured 10 mils of it in a graduated cylinder. So we also have the solvent, which we're going to be using, and this is diethyl ether. So it's in a canister. And then I also measured already the ether, which is about 30 ml in a graduated cylinder. So now I'm going to pour all the mixture. So I'm going to pour the mixture into the beaker, and I also have a stirring rod. So I actually kind of rinse out the mouth of the jar, and then I'm going to rinse out everything to make sure that I got out all the content of the jar. So the ether is very volatile, and we typically use the hood and in the bench hood when you're doing the experiment. So okay, so now I'm gonna add base. So actually what I want to do is first make sure that I dissolve everything first. So I want to dissolve it. So when I add the base, when I extract, I have one layer, so I don't have any particles floating. So in the mixture, there's a solid component. That's why you see the solid particles. And it's also colored. So the three components, I have everything in here with the ether. So in this beaker, I have 4 components. One is the solvent, which is diethyl ether, 30 mils, and I have the three components coming from the jar, which is the three component mixture that we need to identify, separate each one, and then identify what those molecules are. Okay, so I just have like one speck floating, so I think it's dissolved. Okay, and then I'm now going to add the base. So the base again is sodium hydroxide, 3 molar. So I measured already 10 mils. And I'm gonna put it here. And then I'm now going to transfer. So either you add the base in here or add the base in here. It doesn't matter. Okay, so I'm now going to pour this mixture into the sep funnel. So this is the separatory funnel, and I have a funnel also. And then I'm going to now add it. So when you're adding into the sep funnel, make sure that the stopcock is perpendicular and it's closed. So again, make sure that this is closed. Otherwise, if you pour it, it's going to go through and you don't have any container here. So the other way to do that is when you're pouring, to make sure that you're safe, you always can have a beaker underneath. Okay, but just make sure that this is perpendicular, and you should also check that the stopcock will not leak out in here. Okay, so we're going to do again extraction, and I'm going to cover this. So in the upper layer, so I have upper layer and then I lower layer. So the structure of diethyl ether is CH3, CH2, O, CH2, CH3. In this solvent, there's no chlorine. If there's no chlorine, the density is lighter, the density is lower than water. So the diethyl ether, and then you mix it with aqueous solution, is gonna be the upper layer. So that means that in this sep funnel, we now have 5 components. 3 components coming from the mixture, the unknown, and then I added the base, which is sodium hydroxide, and then I added the ether. Diethyl ether is hydrophobic, and then it will not mix with the aqueous solution. So now I have 2 layers. I actually have an upper layer and a lower layer. So we also define this as organic layer and aqueous layer, because the organic layer is the solvent which I added, the diethyl ether, is lighter than the aqueous solution, which is your base, sodium hydroxide and water. The base is going to be the lower layer. The upper layer contains your solvent, which is diethyl ether, and you now have 2 layers. So remember that I am doing the first part in here. So I have the first part. I added ether, 30 mils, and then 10 ml of 3 molar sodium hydroxide to form 2 distinct layers. So I put it in the sep funnel, and I'm now going to extract. So this is where we are right now. First part of the schematic diagram of the flow chart. So again, this is the flow chart of the procedure, and this is also called the schematic diagram, showing you from the top to the bottom. So this is now the liquid-liquid extraction part of the experiments. Again, liquid-liquid extraction is a technique to separate a component. When I added the base, it formed 2 layers. Okay, so I'm now going to extract. So again, the technique is to, again, I'm holding it with my hand, this part here, and then I'm going to invert to release the pressure. So I tightened this stopcock to make sure that it will not leak. And then I'm going to again shake gently and then release the pressure. Okay, you hear that pop? So again, invert, or you can release it up here to release the pressure. So because this is a low boiling point solvent, the diethyl ether, it has high vapor pressure. When you shake it, the gas or the vapor will accumulate here fast. So if you don't release the pressure, this will tend to pop out, and if you're shaking it, it's gonna leak out into your hand. So still wear gloves, okay? So again, I do it several times. Okay, so the pop decreases over time. Okay, right, so do several times. So again, I don't see any particles in my SEP funnel. So it's just basically a reddish mixture and then the base. Okay, so I can release it here also. So I put it back in here, and now I'm going to extract. So I'm going to drain the lower layer and to separate the basic solution. So it's an acid-base reaction. So remember that we have a carboxylic acid and then I added a base. The base is going to react with the acid, which is the carboxylic acid. Therefore, the carboxylic acid is going to go into the lower layer. So I'm actually now in this part here. So when I added the base, the carboxylic acid will react, forming a salt. When it forms a salt, this is now ionic, and then it's gonna go to the aqueous layer. Okay, so again, I added the base. The carboxylic acid in my component, in my 3-component mixture, will react with the base. This is an acid-base reaction, acid-base. So the other product is water. When you form HOH, acid-base, the other product is water. But because we have aqueous solution, the water will just go to the aqueous solution. But my organic component, which is the carboxylic acid, became a salt. This will be water soluble, so it's now going into the lower layer. So we were able to separate the first component, which is the acid, carboxylic acid part of my 3-component mixture, into the aqueous phase. So in this SEP funnel, in the SEP funnel, we have the lower layer containing the base, and then my carboxylic acid portion of my 3-component mixtures. Again, the carboxylic acid is now separated from the 3 components, going into the lower layer, while my 2 other components are in the ether layer. So this is my ether layer. Remember, the ether is lighter, it's going to go up, the upper layer, the organic phase, and this is the aqueous phase. So there's always going to be an organic phase and then an aqueous phase, although the organic phase can be either the upper layer or lower layer. In this case, it's actually the upper layer because the ether has a lower density than water, therefore it's going to be on top. This is my ether layer containing the 2 other components, which are the amine and then also the neutral component in my 3-component mixture. I will now take out the cover, which is the stopper, and then I will drain the lower layer. So there's a layer, the lower layer I will drain into a beaker or into a flask. So I'm now going to use the flask. I'm now ready to separate the layers. So when you are collecting the lower layer to drain it, the tip of the sap funnel should be below the mouth, okay? It should not be too high. The way you set it up is don't set the ring so high because it's gonna spill. So the way you set it up is you have the tip of your sap funnel just right below the mouth of the Erlenmeyer flask, of the E-flask. I also labeled the E-flask as basic, and then carboxylic acid, RCO2H, and then sodium hydroxide. So now I'm ready to separate after shaking several times. So I'm going to turn this stopcock so that it's a vertical, and I'm going to drain the bottom. So when the reddish layer touches the top of the stopcock, I will close. Okay, and close. So this is the first extract. So I'm going to do the second extraction, and again with the base. So the purpose of doing 2 extractions is to make sure that I was able to get rid of the acid component in my mixture by doing another extraction. So it's better to do twice of 10 mL as opposed to one time 20 mL. So multiple extractions, if you are doing multiple extractions, and then with the half of that amount of solvent is better than doing one extraction with that same volume. So again, we're gonna do another base extraction. So I'm gonna use a funnel, and then 10 mL. Again, that base is gonna go to the bottom, and I'm gonna put the stopper and then extract again, so by shaking. So don't shake too vigorously, just invert. The first time you release the pressure, you heard that pop because of the volatile solvent, which is diethyl ether, in my mixture. So invert. Okay, again I'm holding this part here so it's steady. Release. So the popping sound decreases over time. So several times of shaking to ensure that I get the carboxylic acid into the basic solution. Okay, so then again I will extract, let it sit, so you can see that I have a distinct layer again. And then I'm now going to have the second extraction being combined with the first extract because it's the same anyway. So now I'm going to take out the stopper. Okay, and then I'm now going to drain the lower layer. The same thing, combining the 2 extracts. So open. And then I'm watching the layer. Okay, so now closed. So this is our first component, which is the acidic component in my 3-component mixture. So I use a base to extract the acidic component in my unknown. So again, I'm using a base, utilizing the acid-base reaction to be able to isolate my first component, which is the carboxylic acid. So that's my carboxylic acid with sodium hydroxide. So now I have the first component separated using a base. So it's an acid-base reaction because we have the first component acidic, and then I added a base to be able to extract that acidic component in my 3-component mixture. So the other 2 components in my unknown are left here in the sub-funnel. So there are 3 things in here: the ether, and then the amine, which is the basic component in my unknown, and then the neutral component. So these 2 are dissolved in the ether right now. So I have a beaker to make sure that I don't spill it. So in the case that it leaks out, I still have it protected. So I always have a container underneath my sub-funnel. I'm now doing this portion of the schematic diagram. I will now be adding 6 molar hydrochloric acid until it's pH 2. So the purpose of that hydrochloric acid is to replace the sodium so that I get back my carboxylic acid. So I want the H in my structure. Therefore, I'm making this molecule, which is the carboxylic acid, the original structure of my acid, of my acidic component in my unknown. And the NaCl that is going to be formed will just be aqueous. It's just going to be in the water, so I can get rid of that. So the solid that I will form after acidifying is going to be the carboxylic acid in my 3-component mixture. This is now the 6 molar hydrochloric acid that I will use to acidify the solution, because right now it's basic. So I want to acidify it so that I can put back the proton or the H plus into my carboxylate. So I will add it. And then I have a pH paper. So I want the color of my solution to be red in the litmus paper. So this is my litmus paper, my pH paper. So as you can see, when I put the 6 molar hydrochloric acid, it's forming like a cloud because it's reacting acid and base. So there's a reaction. It's actually a little bit warm to the touch. Okay, so that actually is forming like a salt. So it's starting to precipitate out. So it's warm, slightly warm. So I'm slowly adding the acid to neutralize my base. Take note that I'm not really measuring it. I know that I added enough when I form back the precipitate. So I want that precipitate to stay. So I'm seeing some cloudiness, but I want it to stay. That means that if it's not staying, I have not added enough acid yet to precipitate everything. I want the solution to be acidic, but I don't want to add a lot of the acid and then I waste it. So I just want a little bit more than enough so that that precipitate stays. So I can see already some precipitation. Okay. So now let's check the pH. So I can use the this other end. So maybe I should, because it's not yet red. Okay, so it's not yet red. I want it to be pH 2. So I can add a little bit more to make sure that it's acidic. So I can use another strip. Okay, red. So now I can stop, and then we are going to chill this, and then we are going to filter. So right now, I'm going to be isolating the carboxylic acid portion of my 3-component mixture, and the side product, which is the salt NaCl, is just going to be in the water or in the aqueous solution. So the solid again is the carboxylic acid. So right now I have the sample. I chilled it in ice water bath, and I now have the solid portion is the carboxylic acid part of my 3-component mixture. I will now be filtering it. So I don't have to weigh the filter paper because I'm not concerned about the quantity. I'm concerned about that I should have enough solid so I can do a melting point determination to identify what my carboxylic acid part of my unknown. So right now I have the filter paper inside, and I will now filter my sample. I will have the water on. So the water aspirator, again, we do a filtration. The water aspirator is connected to my filter flask. So you clamp the filter flask into a stand so it does not fall all over you. And then I have it connected with a thick-walled rubber tubing, the water aspirator, and now I'm ready to filter. So I'm just going to filter this. Okay, like so. So I should have enough sample, and then I'm gonna rinse it with water. So again, because it's aqueous, I'm just gonna rinse it with a lot of water. So using the squirt bottle. Okay. And then I'm just gonna try to clean it as much as possible using the squirt bottle. The carboxylic acid that we filtered, the color is, I mean, it's uniform, but the color is not as clean, I think. So what I want to do is I want to crystallize this or recrystallize it so that my result for my melting point determination is much better. So I'm now going to transfer this into the flask. I'm now transferring the sample into the e-flask so I can dissolve it. So I added about 10 ml of water to recrystallize the carboxylic acid because the color is not entirely correct. So I decided to crystallize it, and there really is nothing wrong with recrystallization because it will make the sample better when we do the melting point. So now it's dissolved, and I will now let it cool at room temperature and then let it crystallize. The sample already crystallized out, so I'm gonna now again chill it in ice water to make sure that I have everything crystallized. So I'm gonna chill it in ice water and let it sit for around 5 minutes, and then we're gonna do filtration. So I did an extra step of recrystallizing because I want to ensure that my sample is cleaner. If I skip that step, I'm not sure that I will get a good result for the melting point determination. So that's our sample. So before, I already had the this in this flow chart. I already combined the two extracts, and then I was able to filter already the first component. So we're now in the upper layer portion of the extract, and I'm now going to add hydrochloric acid. The upper layer contains the two components, and the two components are the amine and then the neutral. So when I add hydrochloric acid, it will react with the base component of my 3-component unknown, and then it's going to form a salt. Once it forms a salt, it's going to go into the aqueous layer. What remains in the ether layer is just going to be my neutral component. We're back to the subfunnel, the organic layer. So let's review. The organic layer contains the ether, the solvent, and then the two components, which are the neutral component and then the basic component, which is the amine, in my 3-component mixture. I'm now going to add hydrochloric acid, so 3 molar hydrochloric acid to react with the amine. So I already measured 10 mL. And then I'm going to add it into the subfunnel. So once I add that acid into my organic layer, I now form again 2 layers. So you can see it's dark. So the upper layer contains my ether, and then after I shake this, the amine should react with my acid, and then it's gonna go down. So adding the acid will make me separate the amine, and then the ether layer will only contain the neutral component. So the same thing that I did earlier, I'm now going to put the stopper. And again, because I still have ether, which is the low boiling point component, volatile solvent, I have to release the pressure. So you heard that pop again. And then do the same thing several times. So you see that the bottom one is actually getting darker. So the popping sound is still there. It decreases over time, that popping sound, when the pressure is being released. Okay? So now I'm ready to extract and separate. So I'm going to separate the lower layer. Take out the stopper, and then I have labeled here another flask. I labeled that as acid, the RNH2, which is the amine plus hydrochloric acid. So I took out the stopper, and now I'm ready to separate. Okay, I'm going to measure another 10 mL of the hydrochloric acid. So I did 2 extractions. And then again add. So I use a funnel. And then again stopper. Then do the same process. Same process. So we did again 2 extractions of 10 ml of the acid this time. Earlier it was the base. So again, release the pressure so that pressure buildup doesn't accumulate and doesn't leak out into your stopper. Okay, so now I'm ready to separate. Again, take out the stopper to push the pressure down, and then I can separate. So you can see that I have 2 layers. Okay, the top one again, and then the bottom. At this point, the top one contains only the ether, and then your neutral component. The bottom one contains the acidified amine. So I combine with the original extract because they're the same anyway. So I'm now going to slightly lower it a little bit, and now I can separate and drain the lower layer. So now I was able to separate the three already. The previous one we filtered out, remember? And then now this is the basic component, acidified basic component, and the neutral is here. So we're now going to continue with the neutral, and then the last one is going to be the amine. So I'll set this aside. So now we're going to deal with the neutral component. So at this point right now, I have only the neutral and then the ether. So in the diagram, we're looking at this box in here, the organic ether layer, which is the upper layer at this point, which is the in the SEP funnel. So in the SEP funnel, it's the organic ether layer, the upper layer, containing my neutral compound. So we are going to dry this in sodium sulfate and then decant, and then we're going to evaporate the ether. What is left over is my neutral compound. And now I'm going to drain it into this container. So I drained everything. So that is now going to be my neutral component. This is the ether layer containing the neutral component is in this flask. So because we're going to do IR, I don't want any water, because remember we put aqueous solution. So the technique again is to dry this. Drying means removing water. So by adding a salt, which is sodium sulfate, I get rid of the water. So the salt will absorb the water. So the typical drying agent is sodium sulfate drying agent. So I'm just gonna scoop a little bit into here, or I'll cover the bottom, and then I let it sit so that the water gets absorbed into the sodium sulfate. So I'm gonna scoop a little bit. Okay, and then I'll try to cover the bottom, and then I let it sit. So you see, if I don't see anything floating in terms of a blob, that means that it's water. And I can add one more scoop to make sure that I have all the water absorbed. The reason for that is I don't want water in my sample because it will interfere with the IR that we're going to be doing. So I'm going to let this sit, and then we are going to decant or filter into a new container, and then evaporate this, and then we're going to do the IR. So I let that sit. I let the sample sit for about 5 minutes over sodium sulfate to make sure that the water gets absorbed into the salt. So it looks like the salt is clumpy, and I don't see any water at the bottom or anything floating. So that means that I'm ready to filter. So I'm gonna filter it here, or I can decant. The other way is to use a funnel, but because I don't want the sodium sulfate, and I don't want the sodium sulfate to be transferred into my e-flask, then I'm gonna make a filtration apparatus, and I will use again a glass wool. So glass wool, so I get a little bit of the glass wool, and again this is glass. So when you're using glass wool, make sure that you wear gloves, otherwise you might get a cut. It's actually made of glass. So I'm gonna put it in, and I make a plug. Okay, so I push it using the wooden boiling stick, and then I make a plug. And now I'm going to just filter it because I don't want the sodium sulfate. that's my filtration apparatus. So, and then, so right now, at this point, I have the neutral component plus the ether, the solvent, which is the ether. So I want to remove the ether by just boiling it. So at this point, I'm gonna boil it here, boil it off, and I will get rid of the ether. So the boiling point of ether is very low. It's almost just a little bit above room temperature. So I'm gonna set it to just slightly above 30, okay? And then I'm going to get rid of this funnel, put it back here, and then I'm gonna use a boiling stick, and I'm gonna let it evaporate. So I don't want to set the heater too high, otherwise I might evaporate my neutral component. So I just want to evaporate the ethers. I set it slightly just above 30. If it's too slow, I can increase it slightly, but not too much. So the third part of the experiment is now we are dealing with the amine, this part here of the diagram, the flow chart. So the extract from the lower layer contains the amine. So this is this part here, which is ionic. So the protonated amine RNH2 with hydrochloric acid became RNH3 plus Cl minus. I'm now going to add, at the same time I'm going to add a reagent, which is benzoyl chloride. This is the structure, and I'm also going to basify it. I'm also going to make it alkaline by adding sodium hydroxide, 6 molar sodium hydroxide until basic. The purpose of the sodium hydroxide is to neutralize or get rid of the hydrochloric acid and then free my NH2 so that it can react with this reagent. So we make a different molecule. We are doing derivatization by converting the amine into something bigger. So that process makes this amine bigger, and we can determine the melting point later. So again, right now, I'm going to be adding this reagent, benzoyl chloride and sodium hydroxide. We are going to derivatize the molecule into something different. So the amine became an amide. The amine is going to be transformed into a different functional group, which is an amide. So while I'm waiting for this neutral component to evaporate, I can continue the experiment, which is the last part or the third part. This is our third component. So again, this was the, so this flask contained my amine, and then it has an acid. So I'm now going to add the reagent, which is benzoyl chloride. This is benzoyl chloride, and we are going to derivatize the amine, and then we are going to make a different functional group, which is an amide or an amide. And then I'm also going to make it basic by adding 6 molar sodium hydroxide. I will add 1 ml of this reagent. I added a ml. And then, so didn't see anything going on, but there's like a mixture, it's like a blob of the reagents. I want that to react, but because it's ionic, I want to neutralize it by adding sodium hydroxide until basic. So I'm going to use the pH paper again. So I'm going to get 1. Okay. And then I'm going to use a dropper to add my base. So I want this to be alkaline. So I'm gonna stir it. So I'm trying to rupture that blob so the reagent comes in contact with my sample, with the amine, and with the base present, I can expose or I can neutralize the ionic compound, and then I make NH2. So I can add excess actually. So I can see some reaction, I can hear the popping. So the acid-base reaction forming that it's smoky, but I now have more precipitate forming. Okay, so let's check the pH again. Okay, blue. So we're done with the base, and that's already alkaline. So the next step is the precipitate is now our derivative. We made a different compound, so the amine was transformed into an amide. So this is the precipitate, but as you can see, the color is not entirely uniform. So the color is not entirely uniform. That means that there's a lot of impurity in here. So to be able to move forward and to make sure that our product is pure, is clean, you can see that it's not, the color is not uniform. Okay, so we're gonna do recrystallization. So we're gonna do what we did experiment 1 way back. All right, the first experiment. So that's what we're gonna be doing. But I'm gonna let this sit. Okay, it's a little bit warm, to let it cool down. We are now in this box at the bottom of the schematic diagram and in the flow chart. I made or remade this molecule, and we are now going to isolate the product. So it's a solid, this molecule. So it's a derivative. The functional group is called an amide or an amide. So this is now the that product, and then I chilled it in ice water. So I'm now going to filter this precipitate. So the same process earlier. I now have the filter paper. I don't need to weigh the filter paper because I'm not concerned about the percent yield or percent recovery. I know that I have enough so that I can analyze the sample. So now I'm gonna have the vacuum. Okay. Put the water aspirator on. The same setup, filter flask, clamp it. The water aspirator provides a vacuum. So the same idea, I'm now going to filter. And then I'm gonna try to rinse out using the squirt bottle. And then I'm just going to rinse out. So I want to clean it up a little bit more. So we're gonna do a recrystallization step to be able to clean up the sample. So now I turn off the vacuum or the water aspirator. I detach first and then I will turn off. This is now the benzamide derivative that we made from the amine, and as you can see, the appearance doesn't look entirely clean. So I want to recrystallize this. I'm going to transfer everything in here. So I should have enough sample to be able to analyze this the compound. So I'm going to add ethanol. So in the instruction, it's mentioned to recrystallize with ethanol and water. We are going to recrystallize the sample in ethanol and water. So again, in the box, recrystallize with ethanol / water. That means that the first solvent that I'm going to use is ethanol. Then I'm going to warm it so that I dissolve as much as possible my sample, and I expose the sample, the crude sample. This is my crude sample into the solvent, which is ethanol, which is the first solvent. And then I'm going to add water. So this is an example of a mixed solvent system to be able to crystallize a sample. So remember, in the first experiment, we only have single solvent, which is just whatever we chose for part A. But this time, we're doing a mixed solvent system, meaning that we're combining ethanol and water. So when it's indicated ethanol, you use that to dissolve, warm it. So it will not be entirely soluble. It should not be entirely soluble in ethanol in the first solvent. Then when you warm it, you increase the solubility, of course, because you're increasing temperature. And then the second solvent, which is water, should precipitate it out. So this is the ethanol, 95% ethanol. That means, again, it's 95 ethanol and then 5% water. So I measured already 10 mils. So I have quite a bit of the sample, so I'm just going to start first with 10 mils of ethanol, and then I'm going to warm it. Okay, so if I need more ethanol, I can add more because I want this to be dissolved as possible to expose my sample into the solvent so that I can get rid of the impurity as much as possible. So I'm going to crush it, and then I'm going to warm this up. So the boiling point of ethanol is about approximately 78. So I don't want it to be boiling like crazy. So I just want it to warm it up and then to dissolve. I was able to dissolve the sample after heating it for about 20 minutes. And now I'm going to cool it at room temperature. And then we would like to see if it actually would crystallize out, and then we will initiate crystallization because remember we had a solid, right? So we're gonna let it sit, let it cool, and then we're gonna initiate crystallization later on. This is the amine and actually started to precipitate out, so I can add more water. So I added a little bit of water. It started to precipitate out, and then I'm gonna again just put water so the precipitate comes out. So now I'm going to filter it. So again, we're not really concerned about the amount as long as we have enough to do the melting. So I press it. And now I'm ready to filter. Okay. So I'm just gonna let this dry for a week, and then we're gonna do the melting point determination next time. The sample after crystallization. So this is the sample, the carboxylic acid that I labeled. Okay, so after crystallization, and then this is the amide, the derivative after crystallization. So I labeled it's color-coded blue and then red. So we're gonna dry this for a week, and then we're going to dry this for a week, and then we are going to do melting point determination. Took about almost half an hour to get the volume down to this level. So we're left with just really small amount, and I don't see big bubbles anymore from the boiling. And I was able to get rid of all the ether, and then I'm gonna let this cool. I'm gonna give this another maybe 2 minutes. I'm gonna let it cool at room temperature, and we're gonna do the IR. IR spectroscopy will be used to identify the structure of the neutral component. So again, this is the Nicolay IS-10 spectrophotometer. First thing you do is you are going to open up the icon, the application for the IR, which is Omnic. So I double click on it, and then this will show up, and then you just do OK, and then do full view. And now we are going to run just the collect background sample. So we are now going to do just the collect background. So if I hover the mouse on this icon, that's collect background. So I click on it, and then you just click OK, and then it's gonna scan 8, and then this will fill up again black, and then that's the background. So I'm just gonna know to add to window 1, and then it should clear it up. Now I'm ready to add the sample. So next is the sample. I will again put up the what is called the ATR pressure tower, and then I'm gonna move it to this side or this side so that I can put the sample into the hole where the IR light is. So just this is volatile, so I'm just gonna put a drop, and then I put the flask close to the sample holder, and then I put a drop, and then so I put a drop, and then I immediately screw it down, and then I'm going to now click on the collect sample, and then do OK, and then do OK, and then it's gonna show up the spectrum. Okay, so this is our sample. So it's a good spectrum because I don't see the CO2 around here. So I said add to window 1, it's yes. Now I'm going to label. So I will do find peaks. So I hover the mouse over here, find peaks. Okay, and I'm gonna want to label this. So I click the mouse in here. So this is like our threshold, and then I click replace. All right, this one is not showing up, it's actually way down here, so I'm gonna do full scale. So the mouse, I put it here, full scale, I click on it, then I can see everything. So now I'm ready to print. So I'm just gonna do print, okay, and then pull, and then it's gonna come out here. That's gonna be your data. So each one of you will get one IR. So it's gonna look like that, okay? And then you have to compare this with the IR spectra that I posted in Brightspace, and then you identify where the structure is. So in your lab report, you are going to make a table of the absorption bands and then assign the functional group. So this is that unknown. The samples after 1 week of drying, this is actually our carboxylic acid portion of the unknown, and I labeled this as blue, and we added sodium hydroxide to extract it from the original mixture. And then the other one that I labeled red, this is the amine or the basic portion of our 3-component mixture, and this is what it looks like. And this one, that's the solid dry after a week. And I wrote here the structure, so we're trying to determine the R. We know that this is the carboxylic acid part, and then the other sample is the amide or the benzamide derivative, and we know that this portion here of the molecule came from benzoyl chloride. Therefore, we are trying to determine what the R group is in the original amine or the original basic component in our 3-component mixture. The next step is a melting point determination of the carboxylic acid and then also the benzamide derivative. So I will again pack the sample into a capillary tube. So this is a capillary tube, and it's a melting point tube, and it's closed on one end and open on one end. And then I will put the sample at the open end. So sample, and then I will get a glass tubing open in both ends, and I will drop it, the sample, the closed end in here, and drop it off. So it looks like I have enough sample, and then now I'm going to just color code it with a tape, label it, and then it's ready for melting point determination. So the other one, I already have sample. Okay, so I have the tube, the samples in it, and then blue and red. The last part of the experiment is now the melting point determination, which is for the benzamide derivative, and then also for the carboxylic acid portion during the second day of the experiment. So we are now in this part here, and then also this part over here. So right now I have the sample, which I color coded, and this is the blue one, which is the carboxylic acid, and then the red one is the amine or the benzamide derivative. So the lowest temperature for the amine or the benzamide is 99 up to 173 degrees C, while for the carboxylic acid, the lowest melting point is 107. The highest is 182. So again, the carboxylic acid, the lowest melting point is 107, and then the highest is 182. While for the red one, the lowest is 99, the highest is 173. So I'm gonna set it to 99, and then I will constantly check, and then increase the temperature if it's not melting. So the way to set it is you press plateau set, and then I will set it to 99 by pressing both. Alright, and then I press start. It will heat up fast. So I will check the melting of the sample, and again we're looking for a melting point range. So the melting point range starts from the lower temperature to a higher temperature. So again, if it's pure, it's sharp and then close to the actual value, while if it's not pure, if it's impure, the range of melting point is wider and also depressed. So again, this is the eyepiece. There's a lens, and then you look through and then see if the sample starts to melt. So when it's melting, you will see that the solid starts to move, and then it will liquefy, and then you can actually see it clear, and then the sample melts. So you're looking for a sharp change from solid to a liquid state. So I checked, it did not melt, so I'm going to increase it to about 107. Stop first and then plateau set, and then I will go up to 107. Okay, and then start. So now I'm going to check again. So still I don't see anything melting. So the next temperature, if you look at the data, the next temperature is going to be 120, 122. So I'm going to increase it to 120. So remember, there are two samples in here, and we are trying to determine the melting point range of the samples, and we are comparing it to the actual literature value for the carboxylic acid as well as the benzamide derivative. So 120, I will check again. So not yet. So the next one is about 120, 123, and then I will press plateau and then put it to 123 and then start again. So it looks like the carboxylic acid melted at this temperature. So it's about 122 to 123 for this sample for unknown number 4. So that means that I can take out the blue one. It already melted. So if you look at the data in the PowerPoint, the next melting point is 159. And then now I'm gonna do again, I stop it and then plateau again to 159. So the next melting point of the unknown is 163. So again, I stop and then plateau 163 and then start again. So the benzamide derivative looks like it melted at about 162 to 163. So it's quite pure and I don't see the solid anymore. If it did not melt, you are going to ramp it to the next temperature, to the next melting point temperature, which is 173. If it does not melt, you will set the plateau to the highest temperature for the sample, which is going to be 182 for the carboxylic acid. But for this particular unknown, we are done. And now we have the data to determine what unknowns we have in the 3-component mixture. And if you are doing this face-to-face, each student will receive one jar with the 3-component unknown. So I used unknown number 4. Each one will have a different unknown number. So for our purposes, I will give you guys different unknown numbers, and I will give you data which is going to be either posted online or by email. So you will have 2 melting point data, which corresponds to the carboxylic acid part of the 3-component mixture. And then the other melting point data is going to be corresponding to this benzamide derivative. So those are the melting point determination that I did just now. And then the other data is going to be the IR.